scan.
All right, will do. Lecture number 2.
Resistance to being accelerated.
Well,
Advanced
I realize that, but
mechanics.
like, are they actually different in the sense that like if something has mass and
In the lab.
gravitational field, does that mean that it's inertia? Like,
Professor Harter at the helm.
Okay, we're going into the second lecture here, which has to do with Chapter 3 and really Chapter 4. I want to review a little bit just to make sure that the COM line and the difference between inelastic and elastic is clear, because that's part of that first problem. To get that right is important. So what I'll do here is first of all get these things playing, and we'll go ahead. Might as well do it with this one because we may use the third screen here during this class. So I will try to get that going as well. Okay, so the first thing that I want to make sure that you see is the difference between a center of momentum and a center of gravity. The center of gravity is something you talk about in space. So this picture is the last figure in the second chapter, which is figure 6. And I'm imagining the two protagonists in our freeway mishap here, collision, either elastic or inelastic, is being looked at in space and time. So these guys come together, and then if it's elastic, go apart. If not, stick like that. That's the crunch. This is the kabong. So if you were to take a movie of that and draw lines, you can imagine at any point you can balance them. The center of gravity of the system is what you're talking about here. But the center of momentum, the point right here, for example, for the collisions that we did in the first of our things in this class, that is, we started here with this guy going 60 miles an hour, and the poor little VW, as I said, this guy was cell-faxing, and this guy's smoking grass, just drifting along at 10 miles an hour. Here comes an SUV at 60 miles an hour, and if it were an elastic collision, go all the way to here. It's an inelastic collision, so you make it halfway. You end up on the COM line. You end up, obviously, at the point where the velocities are equal for the unfortunate crunched cars that become one mass. 4 plus 1 is 5 tons. So I wanted to just make sure that kinetic center of momentum, which is very similar in its arithmetic to this, that's pointed out around that figure, so you might check that out. But basically you have this as a description of x. This is a description of the velocity, which is the derivative of x with respect to time. That's all the difference there is between them, really, in terms of the calculus. Now, another thing that's clear about this stuff is at first when you use collisions that are both things going along and then one of them's faster than the other, you don't get much difference between the elastic ellipse, the kinetic energy ellipse, and the kinetic energy ellipse that's left after the collision. If you were to remain here, that's where you stick onto this little ellipse. It's very close, you see. So when you do head-on collisions, that there's a big difference between the ellipse that represents kinetic and the ellipse that represents totally inelastic. So the last figure of this is here in chapter 3, figure 4. This is the second half of it, but I've added some things here to make it a little clearer. I just want you to see a collision. This is a stiffer collision. We're talking about something that has a mass ratio of 1, 2, 1, 2, 3, 4, 5, 6. Okay, so we're talking about a 6 kilogram mass or a 6-ton SUV, and that's the minimum that George Bush put on allowing you to deduct the entire price of that vehicle from your business expenses. And the idea was that you would burn more oil, and that would make it nice for the oil merchants. Okay, a little politics here. Okay, rather nasty. And all of these things have slope 6, but we're looking at them in different frames. So we're looking in the original frame, which would be like, sort of like the one that we studied. As you look at frames that are less and less of a speed, say from 0.8, that's this one is at 0.8, then this one's at 0.6, 0.4, 0.2, 0. That's the interesting one, okay? In that case, the potential, I should say the crunch ellipse, the ellipse that results from them sticking. You see, they're pretty close, they're pretty close, they're pretty close. The kinetic energies in each of these cases, it has to be the same. You're just looking at it from a different frame, so physics is not changing. In this case, the current, the kabong, the elastic one has just 0.21 more kinetic energy than the inelastic one. But in this frame, it's still 21, but you go right to this point. If you're totally inelastic, you end up at 0. Okay? And then you drop the speed, make it more and more negative. Well, we're talking about energy, which is that squared, so it'll just be the same as this. Okay, so these are little points that you make. Now, you have to ask yourself all the time during this course, what did I gain by having a roadmap for our algebra? And that's the point of geometry, really, is to set a roadmap that you can study how the equations actually work and what's going on. And the question is, do you just learn anything by that? And I say, yes, you do, very often. It's worth doing. Okay. Well, the same is very much true for what we're going to do today. And what we're going to be studying today is the X2 pen launcher. Okay. Now, I discovered this for my first class that I taught in 1968 at USC, not University of South Carolina, but Southern California. And basically, it's the effect that occurs when you take a pen and stick it into a super ball. This is a high bounce ball here. It doesn't bounce much on this table because it gives a little bit, but and it doesn't bounce very much on a rug because rug takes energy. But when you take this out in the hall, it's more spectacular. In any case, it's safer in here. And one of the things I want to emphasize, if you play with these things, and that's this little product liability disclaimer that I should make for this. And that means that you should be wearing glasses and avoid getting poked in the eye by the pen. But in any case, this is quite a surprising effect, and it was very surprising. I discovered this completely accidentally. And if this had been really a good solid surface, it drives it into the ceiling. In fact, the first time I did it, it's what happened. And I was doing a pen. You might ask, why would I stick a pen in a super ball? It was a mechanics problem of a completely different nature that involved rotation. And the question was, and I'll be giving this problem to you much later when we study rotations, is if you have a sphere rotating in space and you grab a point, just hold it, so it has to turn around that point. Well, what happens? How does it turn and all of that? Okay, and I was trying to do it experimentally because I'm completely frustrated with doing the algebra of that problem. And you can imagine how much more frustrated I got when I did the experiment, which was to stick a little pin in a super ball. Super balls, you know, have this wonderful ability of sticking. They have very high stick friction. So when I spun the thing, and I was hoping to see where the pin would sort of point out what was happening. But instead the pin disappeared, just was gone. And so I started swearing and cursing and that. And my compatriot in another room heard me. He comes in, what's the matter, Bill? And and he said, wait a minute, what do you have a pin stuck in the ceiling for? I looked up and there it was. I forgot completely about that hard problem, and we spent the rest of the time experimenting. This was at University of California, Irvine, with shooting things from dropping them off. You go up to the 4th story and drop them off on the sidewalk and see what happens. Of course, usually what happens there is this ball's like nutty, but it explodes. But when it doesn't, it really shoots. Okay. Anyway, we're going to be talking more about that from time to time in this class, all of the physics of that. But as it came my turn to teach, my first turn to teach them pre-med, pre-dental students who were horrified by the course, hated it. The idea was to make it more interesting, so we ended up actually publishing a paper in the American Journal of Physics, and that's all available on the web if you want to take a look at the history of this thing, and that came out in 1971. We submitted it in '69. It took a while to get it accepted. In any case, the question is, how does this happen? What is going on here? And at first, when I saw it happening, the thing that I did was imagine that somehow a shock wave went through the ball and spit the pen out. Okay, I mean, that's just, talk, right? There's no theory behind that, right? It's like a religion of so not good. And so when I went to teach this class and I wanted to use this thing, I obviously had to figure out how it worked. So if I had a computer like this, there were really no computers available for anything but very difficult work. If I'd had that, I could easily have seen what's going on. And here I'll set this thing up. Now, when you click on, whoops, that's not working there. I should back up here. All that did was advance the slide. Let's see if I can get this guy to run here. So what we're going to do is do what we did yesterday and plot the velocity versus the velocity. But for now, you can go in and get the control panels of this when you run this on your web browser. Instead of plotting V1 versus V2 in that right-hand plot, you can just plot Y1 and Y2, that's the height of the two, and then it becomes fairly clear what's going on. And the basic idea is that this collision completes itself before it hits this one. Now later on we're going to explain how that happens when the pin is actually stuck in the ball, but it's true for that too because the forces are non-linear. That will come up in Chapter 8 of this unit. Okay. But you can see what it amounts to is we need to calculate the second collision in this bump, bump, bang. Okay? It goes down, it really goes bang, bang, not just bang. Okay? And that's the model. We call it the independent bounce model. Okay. Now, let me get back to the original thing, which is this, and point out something else that happened. And this would probably not have led to the Project Ball, which is what this was called. You see television coverage at the time, and made a lot of students. 23 students wanted to get out of the ordinary lab and do something with this. It probably wouldn't have happened if one of the if it hadn't been for a really fortuitous and courageous student, one of the students actually built, after we had done the demonstration a couple of times, a little device that had a magnetic dropper and then a magnetic release so that the ball could go up and we could very precisely see where the top ball went. Now, doing it by your hand jiggles a little bit, so it's really hard to get precision measurements. So to make a project out of it, we need these kind of drop towers. And he built one, then we built some more, and the rest is history. So the next step was, of course, to understand what you get with more than two, and that's a product, which you can buy at Pasco now. And it wasn't patented until 1990, and by Sterling Colgate, who's a colorful character we'll talk about later on. He was completely unaware that this was already published, so we missed out. I'm not a very good businessman. In any case, the first step in this, using our graphic approach, and we didn't have that then, we were doing algebra, and we ended up doing it on a computer. We were an analog computer, and that's a story that we'll take up a little bit later, around chapters 7 and 8. But in any case, what we've got, and this is the graph paper that I put on your table, and it'll be the problem for next week, starting on next Tuesday. The thing is to graph this particular collision, but carry it to some extremes that we'll talk about in just a minute. But the first step in it is getting the concept, that is, to be aware that we're dealing with two collisions, two independent collisions. And all of the devices that you see that demonstrate collisions, such as the ones that are sitting on the desk there, and you all have seen probably and laughed at, this professor was so impolite to call it Newton's balls, but if you drop one of these, it comes out pretty much in making the energy go all over 100% into this. Now if I just take it more like the way Newton really was, I think he had two of them, but if I do this, then you see the kind of collision that asks you for on the first problem of this set, this first set, the number 1, okay? And you've all seen it in pool hall, or if the ball is not having any English, and there's another one here, takes all of the energy out and puts it in to the ball that's hit, right? Well, that's an easy diagram with some 45-degree lines and stuff that you should probably already see in your head. That's an easy problem. What I'm going to do is make an even easier problem, and that's the bounce of the ball off the earth. So what we're going to be talking about here really is a three-body problem. These are the two things that we really work with, but there's another mass upon which they bounce. And that mass is essentially the mass of the earth. So when we're talking about conservation of momentum, it's really a head shrinker, sort of a hair puller to think of the fact that the earth actually moves, or seems to anyway, and including all of the heavy apparatus that you might have in the laboratory that serves as a bounce plate. And the conservation of momentum is momentum disappears into the big object, the Earth. Okay, so I need to see you to see. This is sort of probably a waste of time. It's one of those situations where it's better for you to read about this and look at it. But in the next few slides, I just want to explain why, when we start this, these two objects down, and they're going at the same negative speed of -1. Okay, so on this graph paper that I've asked you to look, the big part of it, forget the little part for right now. There are two little parts to the graph. But on the big one, we're going to start this graph where the actual experiment starts. And that's right here. So I'll just call this start the experiment, and I'll just write start. And then we know that the ball, and we're saying it's independent, I'm sorry, the big ball is independent of the pen, and this is the thing that you might want to label. This is velocity of pen on the high axis and the velocity of the ball on the horizontal axis. So the ball is going to be what was SUV in yesterday's graph here, and the pen is going to be the VW from yesterday's, or last Tuesday's lecture. So the thing that we have to do first is admit or understand why I would move from the start absolutely, or as close to absolute as anything might be, vertically. That is, we're kind of making that an axiom. We're going to make it an axiom that the ball gets its business done without changing the velocity of the pen. So this is the first motion that occurs in this experiment that we're trying to analyze here. Okay? And you say, of course, every time I bounce a perfect thing, if there's no friction loss, it will come right back with the same rebound velocity. But how is that possible when in fact you're dealing with, say, something that's 10 kilograms? That's a lot of weight compared to a super ball, which is only about 70 grams. And that needs to be diagrammed. And that's what I'm trying to do here. This is something you might want to study. It has to do with what I said before. We're talking about mass ratios that are really high. Okay? 70 grams to 10 kilograms if this was floating in space. But 70 grams to 10 to the 30 kilograms, talking about Earth, okay? Not 10 degrees. You know what the Earth value is by any chance? Brad, you remember things like this sometime. Anyway, I have a hard time. But anyway, huge mass. And so the ellipse for the inelastic, or the elastic, whichever, but in the center of momentum, okay, there's tiny ellipse because one side is so much bigger than the other. And we'll be working with some pretty high mass ratios before we're done today. Like to work with 1 to 100, but we'll get to that. The idea is that in any one of these frames, you're going to see almost no slope to that line. There's tiny slope. You see, it's on here it's on the edge of the ellipse. It's got a little bit of slope too. Center of momentum thing. It's got a little slope because these 2 points on these ellipses aren't quite on the horizontal axis. And the same thing down here, only reverse of the thing at the top. So to be honest, to be complete, I gotta say this, okay? And this is the one fly in the ointment for using this, and I hope you do use it in an elementary class when you teach it. But if you have a really bright student in the class, he's going to ask about this, right? So you can't just dismiss it. Okay, well, we're going to dismiss it right now by drawing a line that doesn't have any slope in it, because it's tiny, 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 and we can ignore what slope it does have. And the next step is to draw a graph that represents the second bang here. Well, we're going to call it bang 1, because this was just a start. So our what is the final point for this collision is going to be the initial point. So I'm just going to put a designation here, initial, and you know how we write that. We write it as in. And then, given that the mass ratio of the pen, 10 grams, and that's a typical ballpoint pen, by the way, and 70 grams, which is the mass of these, and these are really old super balls here. They came out in 1964. You can see the date on them. Anyway, 7 to 1 is what we're talking about here, okay? So on your graph paper, what you need to do is use whatever squares you want, but let me just use the small ones here to get started. What you need to do to make a slope of -7 is reduce the speed of the ball by 1 unit. That means the pen is going to increase its speed by 1, 2,